4 times 5, so it would be 2 square roots of 5. Okay, old news, right? Put those phones away, please, gentlemen. So 2 square roots of 5 goes right about there. All right, so 2 square roots of 5. Done. Now what we're going to do is use that information with that triangle up there. That means we never have to pull out a calculator to get theta in this particular instance, even though I eventually will, because I want you guys to kind of see about how big theta is just for reference sake. So check this out. Sine of 2 theta has an identity that you will never have to memorize. You just have to use it accurately. So if you roll up to the top of the screen, say, hey, I've seen sine of 2 theta somewhere. Oh wait, there it is. Awesome. Sine of 2x, or 2 sine x cosine x, and you use it. Great. So 2 sine of x, and theta in this case, cosine of theta. If I am here, it says find the exact value of each function. That means I want radicals, and I want the use of angles in the unit circle. So, and use unit circle. That's, in my mind, that's what it means. It means I need radicals to stay, and I need to use the unit circle to make that happen. Also, there's this little triangle that I drew that allows me to do a couple substitutions. I'm going to go put those in an obvious place. We already know, I'm going to put it in bold red. From that little triangle, we know that the cosine of theta is square root of 5 over 5. Those are swappable. So anytime I see a cosine, I can trade out cosine for square root of 5 over 5. Sine of theta, if I look in that picture, is what? 2 square roots of 5 over 5? There's 2 square roots of 5 over 5. And then tangent of theta, should we get that one? Tangent of theta, opposite over adjacent, 2 square roots of 5 over square root of 5. And since it's 2 square roots of 5 over the square root of 5, the square root of 5 is canceled to just 2. Isn't that cool? Tangent's just 2. I like that one. That is to tell us that all we need to do when I see a sine of theta is we're going to swap it out for its equivalent. Sine of theta is equal to 2 square roots of 5 over 5. That means they are interchangeable. So I take out the sine, 2 square roots of 5 over 5 goes in, take out the cosine, square root of 5 over 5 goes in. The deal is, a lot of folks mix up how this works. You are literally exchanging sine of theta for its equivalent, 2 square roots of 5 over 5. So there is no more sine in it. There is no more cosine in it. It's gone. Like, it's completely gone. So, you good with that swap? Coleman, you're scaring me. I know, but it's taking your full attention. Like, you're like living over there in that world. I can't see you or me now anywhere. So sine of 2 theta is, the end result looks like this. There's a lot of adding and or multiplying that takes place, like numerator to numerator, denominator to denominator. I'm going to write it all out real pretty.
Which one do you multiply first?
That's what's interesting. Multiplication has no order issues. So that's all in the numerator, and then the denominator is just 5 times 5. You can multiply in any order you want. It helps to remember that square root of 5 times square root of 5 is just 5. So that's good. And if that's just 5, I think we just end up with, and that just make 4 over 5, 4/5? How cool is that? So sine of 2 theta is 4/5. Clean and neat. Now, just so you know, the angle itself, theta, is nothing clean and neat. So I would never want to have to go find theta itself. If you do go and get theta itself, it's like 63 some odd degrees. Here, I'll grab my calculator since I have it here. Now, we're going to have to go old school here.
Divide by 2 to get rid of the 2.
Oh, I got all kinds of tricks I can pull off. This is fun, isn't it? Is it in focus? Oh, yeah, here we go. I'm going to try and do it while looking through the camera window. This is going to be funny. Do you guys remember the triangle that I drew in the beginning? It had a particular look to it. Isn't it cosine of theta was square root of 5 over 5? You can use that if I write cosine of theta square root of 5 over 5. Right, that was what I had. And you remember we do arc cosine of both sides? Like that? Okay, so that's what I'm going to do in my calculator. I just want to know what the angle is. I'm just curious. You got to be in degree mode because it is a degree thing. So I do arc cosine square root of 5 over 5 just for reference, not fanciness. 63.43 degrees. I'm going to stow it. Use the storage button. If you haven't started using this for big decimals, do it. Hit store and then pick a letter. Alpha A is good enough for me. And now I don't have to remember what that angle is. But the biggest thing is that is my angle, 63.43. The picture I had that I drew in there, I don't need this. If you want to see that the identity is true, that might be nice. Like sine of 2 times A. That's the first. That's what we just did. You get 0.8. Is 0.8 4/5? It's totally 4/5. If you use the identity, which was 2 sine cosine, so 2 sine A and cosine of A, is that the identity? Oh yeah, 0.8. So all that stuff's equivalent. We just did it exactly. The angle's 63.4349. It's not on the unit circle. It's nothing fancy. It's just we can do these exactly. That means no calculator involved. The calculator will reinforce it, but it's totally nicer without it. Okay, so back to work on what I was doing before. So click, click, click. Let's get back to where we were. Okay, onward. This. Come on, Notability. Keep up. It's back. Okay, so down to where we were. We love the unit circle and we love radicals. That's why we used them all over the place on here. Cosine of 2 theta works out as nicely. All it comes down to, we just want to trade out any cosines for square root of 5 over 5. Sine 2 square root of 5 over 5. Tangent, trade it for a 2. That's it. We get to put those in wherever they belong. And that becomes the moral of the story. So cosine of 2 theta, don't memorize it. Look at the sheets. There's 3 of them. So when you're looking for cosine of 2 theta, you get to choose your favorite. And I don't know, do you like, this one looks nice. Let's go with that one. And I picked it because it has something I also want to show you inside there. But there's no reason to pick one or the other. It just is. Later on when you're doing it for simplifying purposes, there's sometimes a good reason for one or the other. Thing you have to know. Did you guys know cosine squared of theta, I used an x, sorry, on that one, is the same as cosine of theta quantity squared. That is not always remembered. Put theta in there. So when you have a little squared, it means the whole thing gets squared. That's a good thing for us because now all we have to do to evaluate this is replace cosine of theta with square root of 5 over 5, and we're good to go. So 2 and then square root of 5 over 5 is equivalent to cosine of theta. Square it, minus 1. We're essentially done. So we get cosine of 2 theta, whatever theta is. We know it's 63 degrees, roughly. Is square root of 5 gets squared, and so does the 5. So that makes 5 over 25. Right? And 5 over 25 is 1/5. So I get 2/5. And I subtract 1 from it, but I'm going to use 5/5. And that's important. So if you're wondering where this 1 went, it's now 5/5. And that makes negative 3/5. Weird. Negative 3/5. So what's the deal with that? Like, what would that mean in the context of this? This actually has some sense. If theta is like 63, wouldn't 2 theta be like 120-ish something? We just found out that if I go to 2 theta, that angle there, it says the cosine there would be negative 3/5. And all that means is, hey, did you know that the adjacent would be negative 3, the hypotenuse would be 5, hypotenuse is always positive. That means we'd have a little triangle over there that's like negative 3 for the adjacent and positive 5. That's not too bad. That looks reasonable. No, it's not drawn to scale. These 5s should probably be the same length, but the idea is you're in another quadrant and you're just getting the values of some other angle that's in there. But not necessary. It's just, so far it kind of fits. It's not outlandish. It's kind of sensical. It's just kind of fun. Sine of theta over 2 is another identity, and even though it's at crazy angle, 63.43, I can get an exact value for it. So all we're going to do is use the half angle identity, which is up top here. There's a couple options. Thankfully for sine of theta over 2, there's only one choice. But look what it has inside. It's got this cosine, which is awesome because we have a thing for that. We have a replacement for that cosine. So we're going to go use it. 1 minus cosine over 2 in a radical. So plus or minus 1 minus cosine all over 2. That cosine is the thing that we get to replace. And we know what it replaces with, square root of 5 over 5. So that's the replacement process, and we know and love it. And Master Davis, what are you going to do?
I thought you could have a radical inside a radical.
Ooh, you can have radical inside a radical. What are you talking about? I love radicals and radicals. Yeah, I think there's some old rules about like how you write things. Totally calculable. We'll show you at the end it's accurate.
All right.
Some of the rules, like even rationalizing the denominator, are from pre-calculator days. Kind of go back to like using a slide rule, and then it became good form, and then it just became kind of standard practice. Doesn't change the result. And so the manifestation for you, we have to mess with it for my math lab sometimes, or rewrite it for simplification to make your lives better for whatever reason. For me, I'll show you what I want. I want you to go far enough to get these things that need to be subtracted, like the numerator has a subtraction in it, take care of all the subtractions. Combine those. So this ends up being 5/5 minus square root of 5 over 5 on the top over 2. That I want to see that, and I'll show you why here in a minute. You can get really close to simplifying this. The top would be 5 minus the square root of 5 over 5 if I put those two together. This little process that I went through, I'm going to highlight it in yellow. You want to do every time. We're going to do it about 3 times in a row here. Seeing that, rewriting it, and then rewriting it again. It does look like the golden arches. It's amazing how we've all been kind of, I don't know, McDonald's all has us under its power. I'm sure right now they're like watching us, saying, when is he going to be hungry for that next cheeseburger? How can I market it to him? Somehow they made me write that, is what I'm thinking. They controlled my brain. They're using the little like camera here. I bet that's what it is. It's okay, McDonald's. I'm not even going to fight it because I do like hamburgers from McDonald's. So it's okay. This is the next piece. Stay with me, stay with me. We're here all day long doing notes, so I know I'll give you a little break, but all class long. Be prepared. Do you guys see that 5 and that 2, the divided by 5, the denominators? Once upon a time, I helped you guys figure out that piece. Do you remember when I said, hey, if you get a 1/2 inch and you cut it in half, what do you get? 1/4 inch. We all know this. So if you divide it a half in half, you get a 1/4. And what happens is, if you recognize, we end up multiplying those denominators. If you have something with a denominator and divide it again, it multiplies that effect. So that little expression right there, that divided by 5 and then divided by 2, is going to become a single denominator of 10, 5 times 2. That's an important process. We see it a couple times. That is awesome. Now, Davis mentioned about this radical and a radical. Once upon a time, there's rules for that. I am perfectly happy with all that. That's actually a very healthy response. It's accurate. For fun, remember where we started? It was the sine of theta over 2. Now, if we go to look at our picture, sine of theta over 2 is actually saying the sine of, half of this theta here. We're cutting in half. So it's like 30 some odd degrees. I don't know, like 35. No, I'm sorry, like 31 degrees, 31 and a half-ish. Not that I need to know it, but it's the idea is that's how big that's talking about. And we should get sine is, now it says equal to plus or minus. Because of the picture that I am referring to, the fact that I know what I'm drawing and where this is from, and I can't get my 2 fingers to work, the fact that I know where this triangle exists means I actually know whether this is plus or minus. since sine is the y coordinate,